Okay, hello. I'm gonna be doing a little bit of a overview on the automatic rocker design that I did for the TETRA nonprofit. Kind of go into a little bit of why, and then really mainly focus on the how of all of this and kind of how it's done in case you want to recreate this for whatever reason, whether it be for accessibility or you just want something that does an automatic rocking motion. So let's start where kind of all of this begins. There's a nonprofit in Canada called TETRA. It does like custom assistive technology and kind of wide range of things for people with disabilities where they can't find commercial solutions. So things like custom cribs, you know, accessible washrooms in homes. There's been a bunch of tricycles I've seen that have been adapted, and a whole wide range of things. Um, there's lots of other organizations like one I work for, Makers Making Change, that does this work as well too. Kind of different scales and levels, and we focus on a bunch of different things. But I've been volunteering for TETRA for 3 or 4 years now. I did a couple, kind of easier projects at the beginning. And then this one's been the majority of my time volunteering for them. So, I mean, it's been fantastic. The family that I've been working with has been great. And kind of, the background on this is there's a family who's a child, who's fairly young. Try not to give, too many identifying details. But, in that, like, 5 to 10 range, who was born with a various disabilities, a really rare condition, um, combination of a lot of different factors, and he used like a child's rocking chair for the majority of his life while he was feeling. And he has kind of like week long stints while he's feeling ill. Um, and when he was in the rocking chair, his parents would push him and would kind of take shifts, like almost 24 hours, try to cover, or more than 24 hours, but around the clock, trying to kind of cover that rocking motion for him that would help kind of soothe him when he wasn't feeling well. And this happens quite frequently. Again, I'm paraphrasing a little bit, but yeah. So that's kind of the thesis of this was, okay, let's get a bigger rocking chair. Let's get like one that's going to suit him for extended amount of time, and kind of meets all of his occupational therapy and positioning and seating needs. And then also let's make that rock automatically, so the parents don't have to take shifts doing that, or they don't have to do it manually. They can just kind of check on something that's going to automatically do it. So I'm not going to focus on the creation of the rocking chair itself. That was a long process and was something that as myself and Cody initially, another volunteer at Tetra, were kind of like figuring out how we're going to do this. And at the time I was in university, and kind of realized we weren't furniture designers pretty quickly. So we just ended up working with the family to connect them through their occupational therapist to a furniture designer who could make that. So kind of like a clinician user-led design that came from the furniture maker. That took multiple years to get actually manufactured and built, but then it was finally built, and then now it's been kind of my responsibility here to build the automatic rocking portion of that. Okay, so that should be the most amount of talking without actual videos to show here. I'm going to show kind of what the final result looks like, so you get the idea of that first here. So this is a child here in the custom rocking chair with the right padding and all that stuff, covers and everything. And then you can see this green box and this wooden arm that's going out, that's actually rocking the chair. So that's the automatic rocker that I designed. Has various speeds. Right now it's going probably closer to the faster speed here. You can see, and it's working well. Based on his like growth and stuff, maybe we might need to think about getting bigger chair again, but something like this arm, will be able to, adapt to those other sizes. You might need to change the arm length, but that's a very kind of easier thing to change. Okay, so that's kind of like the, why and kind of, the purpose of all of this. Here's a little bit of a closer look at the solution. So we got a RAM arm connection here on a RAM clamp. That's going to the back chair bar. That's rotating on a motor here on like a crank arm. And that's all in a 3D printed housing. And that brown box here has all the electronic controls for speed control and current and all that stuff, which I'll get into. And you can see here you can turn the dial, left or right to get it faster or slower. There, so you can bring it right down to like, super, super slow, like barely crawling. And then all the way to kind of like the fastest desired speed that, they'd need. A couple other features on there that I won't get into when we look at the CAD. But that's what we're looking for. So if you want to make this yourself, you will need a bunch of different things. The first one here, let's close that. The first one here, you're gonna find everything on my GitHub. So I uploaded, again, at Makers Making Change, we have kind of like a template of how to upload open source designs and kind of show them. So they're in these like folders. If you want to just get a zip file, you can go to code, hit download zip, get every file that you need to make this. So 3D print files, so all the 3D print files, all the build files I need, both in Step and Fusion files. Use Fusion for the design. Documentation. I didn't make a full assembly or user guide on this. Again, the purpose of uploading these designs here is so someone can make it if they want to. I think that this is a very niche device. If there is higher demand, I'm happy to make an assembly guide and kind of go through that, but I just don't think it's really worth the effort at the moment. And this will kind of serve somewhat as that, because I'm going to go through kind of step by step, how to build this thing when we look at the CAD. So hopefully, watching this video, look in the files, you'll be able to get all the stuff that you need to build it. But if you have any questions, email me, DM me on GitHub, or add a note or issue or something. I'll find it. Email is tylerfentie@gmail.com. tylerfentie@gmail.com. So the documentation of the bill of materials, you get a full kind of Excel sheet here of all of the components that it took to build it. Estimated mass of the 3D printed components, so you can predict how much filament you're going to need. Brief overview of the tools, and most importantly the links to everything. Mostly everything is Amazon. One thing I got from a local shop, but if I was going to rebuild this, I would actually change this part. Again, we'll get into that, but yeah, Home Depot for plywood. Skateboard bearings, you can buy at any skateboard store. Bones Reds is what I used here because that's what I had available. Arduino Uno, which you can also get from Amazon, I believe, but I got it right from, I already had one here, so I didn't need to buy one, but you can get it right from Arduino. So you order all the parts, you go to the bill of materials, you get all the parts, ready and shipped to you. You buy them yourself. Then you go to the build files. You can open up the CAD, make any changes that you want. Then, if you made any changes, export those 3D print files. If not, go to here, go to your 3D print files, download all the 3D print components, print them out however you see fit, and then assemble it, as I'm going to talk about here soon. I am not an electrical engineer by any means, and that's going to become very evident right here. This is my electrical schematic for all of this. Yeah, I'm sure some of you are probably shaking your heads right now if you're into this stuff a little bit more. But this worked for me. Basically, it's just I needed something that I could draw on, that I could kind of play around with, because again, the biggest well, the biggest challenge I had was this design was, learning some of the electrical components. There's been a couple different versions of this, and this was definitely the most sophisticated when it came to the electrical side of things. So you got the schematic, how to wire everything up here. Again, might not be, something you'd want to, do on a job, but good enough for me. So yeah, you got that electronic schematic. And then you get the code. So the code that goes on the Arduino that runs everything, basically does the speed control, the automatic shut off on the overcurrent. So, if the motor starts binding or the current gets too high, which is indicating something's wrong, then it'll automatically shut off. And there's a reset button, which I'll show a little bit later when we go back to that beautiful schematic that I have there. So, because I haven't made this video yet, it's not here, but there'll be a link to this video here. It's under Creative Commons Attribution Share Alike 4.0. So, anything that you see here, feel free to use, retake, remix, and do all that different work. And, a lot of the, templates I use to make some of that documentation is from Makers Making Change. So some attribution there, and that is also share alike too. Okay, so that's everything you need and how to look for it. We talked about why this is important, and now it's time to get into the design. So there was, again, many iterations of this project. I'm sure a lot of you can think of easier ways to do something like this. This seemed to be the most, kind of simple and practical for long-term usage. First design that I had on this upper piece, that I had like basically a disc that had a rope attached to it, and every time the disc would rotate, it would like pull the rocking chair down. That the way this rocking chair is designed, it doesn't have a very like steep curve or parabolic curve here. It's quite shallow. So when you would pull it down in one position, it wouldn't be enough to let it kind of go back, forward. It wouldn't even really reach past neutral. So good in design, good intent, but didn't rock the way that the family wanted it to. The second design was, kind of more, okay, well, now we need to learn how to push a rope. Let's make it not a rope, let's make it something sturdy, and we'll kind of go from there. So that design was very similar to the one that you see here, except for it didn't have speed controls, didn't have overcurrent, and the motor kept binding. It was an AC motor, and it wasn't very smart. It was just a motor plugged into a wall with an on-off switch, and it kept binding, wasn't powerful enough, and all those things. So then now, kind of this version was like, okay, let's actually look, at the path that we need to create. Let's kind of learn from everything that we did there. I'm also lived 3 hours away from the family, so it was really just like, go there, learn as much as you can on this test, go back, try to fix everything, which obviously you can't, doesn't happen. So you go back, try something else, and then, you just kind of go back and forth, which was, great process. Family, again, is amazing, and they're really friendly, and we're open to, designing this. Again, started these designs when I was in university, so a lot of growth here on some of that stuff. So this was something I made in DaVinci Resolve and a video editing software. I basically tracked the middle of this top bar here in the path that it goes in the motion that they wanted. So like kind of fully where this front tip is on the ground and fully where the back tip is on the ground. And it ends up being, I think, was somewhere around like a 40-degree angle. I can't remember the exact angle now. And you can see there's a little lifted there and maybe a little curve down here, but for the most part, it's pretty straight. So yeah, that was a good kind of validation of what we needed to do. So this is what I came up with here. So we're just gonna go through this piece by piece here and just explain kind of what these components are. This red bar and this blue piece up here is just like the path that you just saw before, where this blue thing is at 40-degree angle, and then this bar is just simulating what the bar of the rocker would do. didn't want to model the whole thing and the rocking motion and stuff, so this just gives you a good enough approximation. These two are linked together with a joint because so then you can kind of show that motion. It's like a revolution joint or revolve joint around here. So basically, if you look at this linkage piece, it would go here and then go fully around this bar. But I cut that piece off after, so the joint still stands, but you can kind of. But I was able to get an actual kind of model of what I want the linkage to look like. But I'm getting ahead of myself. That's what this is up here. So if anything, we can kind of just forget about the bar and the rocker here, because these are the components that we have. We have two little small floaty components down here that are just used kind of spacers. Less important, but we'll get to them. Okay, so we start off here. Let's move everything off. Start off here with this pink kind of salmon color base around here. So this blue kind of like knob is simulating the thread that came out of the motor, and then that is I had to call it or a connector nut threaded on here, and then that went onto a crank arm. That went to a shoulder bolt that was threaded through, and then bearings were in between here that allowed this to kind of move around as you saw in the video. So the motor sits in here, and then with these three bolt holes, it's able to fix there. So that's just something that came right from the motor. I have a photo of that here. This is just a test print when I was testing for alignment. So you got the motor here and three holes, and then those bolts came with the motor. So just made a little faceplate, and then you can see that's the connector nut there that I forced through this crank arm is what I was calling it, and then I put that shoulder bolt on there. So before you actually would put the shoulder bolt on there, you would slide the bearings through and the wooden arms that would go to the rocker. But that's basically what that connection looked like. So that's kind of the main housing. Some other stuff on this side, which let's actually just get to that next. So that here is this electronic housing box. Yes, it is ugly. Yes, it is bigger than it needs to be. This was just one of those, like, I had this thing laying around, and the cost, I mean, again, it's a volunteer project. TETRA, is supporting and paying for these materials. So, budget was definitely a constraint here. So this is just the size of the proto board where all the electronics fit on it. So I put that in this 3D printed housing. This is the Arduino in another housing here, which I don't think I don't really have a joint to animate that, but this slides in on these dovetail kind of joints. So you got this kind of electronic housing here that slides onto, again, these other dovetail joints here that are coming out of the main housing, and then those rest on these kind of extrusions that I made on the bottom, just so it doesn't go all the way to the bottom, and adds a little bit of support there so it doesn't hang off or do something weird. And then you got the lid there that goes on and protects the housing cables and stuff. Also has some cutouts for the potentiometer, the on and off switch, the power like adapter thingy where you're plugging in the 12-volt power source, and then a reset button. We'll get into what all those do. We're just looking at the components here so you can get an idea. Then we got a base that goes on underneath it. So the ground is here. It's just the way that this is the main parent component. So this goes on. Inside here, there's a bunch of empty room, and that was filled with sand and metal chain to add some weight. So just on the motor and the electronic housing and all that stuff itself, it's not heavy enough to not kind of rock with the rocker or get pulled along in its way. So I added this weighted base here that fits on and does have three holes for mounting holes. So on the top here, You can see there's a matching ones. So you would put your bolts through there so the base doesn't fall off. It's all just kind of becomes one unit. It's just got a false bottom, so you can add some weight. Okay. Then, so you have all this stuff. Now we just need to close it up and add a lid. So we got this sliding component here, which also has thread or holes here. That then you would put a bolt through, and on any component that you see here that doesn't just has like a regular hole that you think you would thread something into. I put threaded inserts on all of these heated inserts, heat threaded inserts. Probably saying that wrong. Brain's not working right now. But yeah, you put the threaded inserts in there, and then I just with a soldering iron heated it up, pushed it through the 3D print, and then you could put some other stuff, and then you could put the bolts through it. So I think I can't remember the exact size. I have checked the bill of materials, but heat diameter is 4.4. So yeah, I think we're using. I have to check the size of the inserts again, and add that to the bill of materials. So this here would slide down. So this basically just kind of like, we got the 3 bolt holes on this side to keep the motor in place. But the back side also just so it doesn't rumble and shake. And so this piece is covered here. And then also there's this insert here for a fan, for like a 40 by 40 by 10 computer fan. The motor never in my testing got even close to like operating or past like its operating temperature or anything, but again, the family might be using this for extended periods of time, so added that there. You put the housing in there, and then this little cutout and this little cutout on the side here is for the cables to kind of run through. Again, not the prettiest thing in the world, but did the job. Yeah, heat kind of vents on this side. Yeah, so that slides down, and then you just cap it off with the lid, and the lid goes on there. And yeah, there's a little bit of a gap there because again, wires and stuff coming through, and I didn't know if there was going to be, well, there was a little bit of like the support material that goes through here, so this didn't actually fit completely flush. So I wanted a little bit of play, so the bolts have some room to go, and again, a little bit more heat escape there. I mean, you have this massive thing open, so it wasn't really an issue, but yeah, wasn't concerned about well, I wanted that play there, basically. That's what I'm trying to say. Okay, then you get to linkage arms. So the linkage arms have let me see if I can get a good view here. Right here. They both have cutouts for the 22 millimeter outer diameter bearings. So you'd press fit those bearings in, and then that just kind of becomes one thing. You could make these linkages out of anything. Ideally, I wanted to make it out of acrylic, so that press fit would be a little bit more exact. It would look cleaner, be a little bit more rigid than wood. But again, cost and time constraints. Ended up going with wood, and then if that becomes a problem for the family in the future, then we'll talk about that with TETRA and see if we can get a acrylic solution. So I don't have it modeled here because this was kind of a last minute thing, but these are spacers here that go in between the 2 linkage arms. Mainly for stability, but also so then at the very end here you have a linkage that you can attach those RAM components to. So we go back to that video. So you can see all those green 3D prints there. They actually have metal inserts inside of them. That just was kind of my mistake. Like the 2 nights before I was going to deliver this, I ordered the wrong size, like aluminum spacers. Supposed to be 1 inch by 1 inch is what I wanted. So they fit on the RAM components, but I got 1 inch long, but half an inch in diameter. So these RAM components wouldn't fit. So I just press fit all of those metal inserts into these plastic pieces, and then add a little bit more rigidity to it, and now you can clamp this upper arm to it. So what's not modeled is this RAM connection. I mean, look at it, and I didn't want to model it. I work with RAM components a lot at work, so kind of expected and knew how they'd work. So I just kind of measured this length, and then took that piece off of it there. So yeah, you got like a U style connector that goes to this double-ended socket, and then that's going to the chair. So this connection is really rigid. This connection is really rigid, but this middle one I leave a little bit loose because as you can see, there's a little bit of like hinging and stuff that happens right here, which is, these RAM components work really well for that. Definitely something that could have been designed, but for the cost of the RAM components, not worth designing that if these work as well as they do. And again, down here you can see the crank arm, the bearings going on that shoulder bolt, and yeah. One of my coworkers made a really good point here, that this piece should be covered with maybe some flexible plastic, like a kind of rubber cover or whatever that is, just so it doesn't interfere with the linkage, but also avoids pinch points. Totally agree with that. And next time in Edmonton, we'll swing by their place and see if we can get that done. You can see here those cables, running through the right pieces, and then that fan component in that base. I know there's a better. There it is, right here. Fan component, wire going up through here, and then these two blue wires are going to the motor. The batteries here. So this was a design flaw on my side. So the power is coming from the 12 volts that ends up powering basically the motor driver and the motor, but not the Arduino itself. It gives some power to the Arduino, but not enough to run it. That's my circuitry design issue. You could definitely have just like one power source going in and run the whole thing. However, this just goes, to kind of the more motor components. This battery, you can plug into the Arduino on the left here, and then run the Arduino off these batteries. Works totally fine. However, I found the batteries, died a little bit faster than what the family wanted, so I supplied them with a cable that goes directly into the wall outlet through USB through the Arduino too. So the Arduino is being powered through the wall, and there's also another 12 volt thing going to the wall. So two things going to the wall. Power saving thing is kind of a nuisance and non-ideal scenario there. So that definitely could be improved. That's an opportunity for improvement there for sure. Let's see if I can get a still of the electrical design here. I don't think I'm. Oh, there you go. So, yeah, you got the reset button down here, on and off switch, power input, and then the potentiometer to change the speeds. The on and off switch is basically just a kill switch. You hit it shuts everything down, immediately. If the motor starts binding again, that current goes above that amount, a relay switches on, and then power's still on and stuff. It just completely stops the motor. So you just tap this red button here, and then it will start going again. That was a concern on the second version that I went and tested with them. So this was kind of the improvement for that. I don't think I'm kind of missing anything there. So that's kind of like the housing design. A couple nuances and stuff you'll find if you're looking through the designs. And again, it's open source, so take it, remix it, make it better. All those things. Definitely not. This is not like the best version of what this could be. So let's take a look back at not the programming side, the electronics. So we got the Arduino, the brains of the operation here, and then we got a motor driver that is supplying all the extra current and voltage and all that yada yada good stuff that the motor needs to run. That is going to that on and off switch, and then I also have a 25 amp fuse there. So if the current sensor setup that I have there isn't working, the overcurrent sensor, it'll blow the fuse first if it goes past 25 amps. So that's another safety protection piece. That's the power that's coming out. You got brains and computer stuff going to the Arduino, brains and stuff going to the Arduino from the current sensor. So current sensors up here, relays down here. Try to label those as best as I could, so if you get those parts, you'll be able to figure out what wires go where. We got the fan here on the bottom. We got the tactile switch here, the reset switch here, and then the potentiometer on the top. Again, not standard notation, not standard drawings, but it should be enough to go. In the middle is the proto board, or like the solderable breadboard. So the black lines are ground, red lines are the positive. That's coming from the Arduino, the 5 volts, or the 5 volt reference. It's going there, and the ground is coming right from the motor controller there. So you have like a true ground, you got the 5 volt reference, and everything is referenced off of that. That was a big, kind of issue when I was troubleshooting this, is I didn't have everything on the same ground, and ask me how I know that. So that's kind of like the layout electrical design. So the proto board, the current sensor, the relay, the Arduino is all like in the motor controller, and the motor all hidden in the enclosures, and then the potentiometer, tactile switch, the fan, the on and off switch, and the power input, and the power input and for the Arduino are all showing outward. Also that the USB is showing too, for the reason of this. We'll see if I can. Let me just pull up that Arduino code here quickly. V4 final. Okay, so if you're looking at the code, the main thing that, like, if you're using this yourself, the only thing that you're gonna have to change is the value. No, which value is it here? Down here, your sensor value. So this is the threshold that you can set for the readings that are coming in from the current sensor. So when you have the current sensor going, and it's operating, it's gonna be reading whatever value it's reading. Say it's all at 400 to 500, right? But then you put a lot of load on it and starts binding, and it gets past 600 when it starts binding. You can set that threshold, so anytime it gets near 600, it's gonna stop. So this required a little bit of like playing around with when I was there doing the setup. I had the laptop out, and then had the kiddo on the rocker, and initially it was shutting off because the value I had was too low. So you're just cranking it up until you feel like it's in a safe location where that is. Bunch of other stuff happened in the code, but basically that threshold here is the value that you want to change. Everything else should be totally fine, unless you want to change the way the potentiometers doing the different speeds and everything, and the PWM range and all that other stuff. But yeah, that's the code. That really should be everything. You got the programming, you got the electronics, you got the documentation, you got the build files we went through, and then the 3D print files. These aren't in the orientation that you would want to print them in by default. Every printer is a little bit different. These are all the 3D prints on my Bamboo here, for example. So first build plate, you're looking at somewhere in 11 hours. Next one, you're looking at 10 hours, about 2 hours, and then 6 hours. So it definitely takes a significant amount of time here, cumulatively, to put this all together. Really, the only support is required is this sliding bit here. I printed in this orientation and had the film in here, but you could definitely flip it and do it the other way. Whatever you want to do. And again, took like about a roll and a quarter, roll and a half to print all of this. So again, substantial printing for some design like this. But yeah, that's really it. At the end of the day, it worked. It's still working, as we know right now. And if there's changes and stuff we need to make in the future, it's totally fine. Happy to work with the family on that. If anybody has any suggestions or questions or whatever it is, again, feel free to contact me on any again the GitHub or my email that I mentioned before, whatever that is. But as you can see here, working well. Kiddo's happy. He's got an automatic rocking chair. So that's all I got for this. Thank you.